So today, this is week 11, I guess. Today we're going to do some packages. I'm going to back off a little bit on what I was doing and just sort of show how to do it. And I think that instead of spending lots of time on that, one of the things on the project session is to actually create that first package yourself, a trivial one, just to make sure you can actually really do it. Now, if a bunch of you have already done that, so I don't know if that's going to be completely, but there are other problems to work on then too, if you've already done that. Okay, so packages, and now then we're going to finish the primary decomposition. In other words, going to do the non-zero dimensional case and figure out how it all works together. And then we're going to do the Eisenbud, Hunicke, Vasconcelos, which relates associated primes to X and allows you to calculate it without computing a primary decomposition. So, which is in fact still the only way I know how to do it. So let's see. I think I have to. Oh shoot! Again, I have to join the Zoom, and I don't have the link handy. So, okay. Okay, so we're finally at the Macaulay 2 doc. Okay, so let me remind you how we got that. So I pulled up view help, and I see this page here. Let me make it a little larger, and I'm going to go to Macaulay 2 documentation. Okay. And I get this thing. Okay, this is these are probably some of actually that email address is out of date for him. But in any case, we have all this stuff for the new user getting started, all this kind of stuff, right? But I would just go down to packages provided with Macaulay 2. Okay. Again, let's make it larger. Is that large enough to see? Okay. So here's a list of the packages, and these are done by keyword somehow. So ones that are mentioned algebraic geometry and so on. They have all of these different things. There is one that we're going to look at later called documentation. And actually, there's a mistake. Someone put that documentation in the keywords. They put that into there. So instead of being placed into probably commutative algebra, it got placed here. I just noticed that last night. So, but anyway, okay, so there's all these things. This is a little easier list. It's still a kind of overwhelming list, but at least you can sort of go through and take a look at it. Okay, now where I'm going at with this is I'm going to the end. Oops, I can't see this. There's this thing called packages, Macaulay 2 packages. I'm just going to go to that. And now this is some documentation. That's not what I thought I was going. Whoops. I'm trying to make it larger. Okay. So here is a package. Okay, it talks about a package. And then it says using existing packages, creating a new package, writing documentation, and debugging a package. Okay. So using existing packages, that's fine, but we're going to go to creating a package here. Okay. And now this talks about a few things. It says, if you read it, which we don't need to completely do right now, but there are 5 parts to a Macaulay 2 package. There's the new package header. That's the first thing you have in your file. And then you have a list of exported functions and variables, which we'll take a look at. We have the actual code that is really what you're doing this for. And then you have a begin documentation thing, and you put your documentation after that. And then you have a bunch of tests. Okay, so that's all a package is just these list of things. Here, there are 2 things here though that are good. An example of a package for a basic template for a new package, or package template for a utility for generating the skeleton of a new one. Which way you do is really, we're going to go to example of a package. Okay. Okay, now let's make it larger. ignore this first line. That really shouldn't be here, I don't think. But in any case, here's a basic example of a complete package. And what we're going to do is I'm going to try to select all this and see if I can actually run it. Now, it could be that because sometimes when you select from a web page, quotes get all messed up. And so it might not work. We might have to do it slightly different way to get it. But anyway, here it is. So let's just take a look at it. Before doing it, there was the new package thing. That has the name of the package as one of the arguments. You give it a version. You typically start it at 0.1. And oftentimes that's where it stands in even when it gets released, it should be at 1.0. But at 1.0, you're telling everyone who might use it that we're going to try to not change the interface on you, capriciously. It's a string. It's a string, 1.1. You could call it whatever you want, which is annoying because it probably does do lexicographic comparison on strings to see which is larger, and it does it in a way that will compare numbers correctly. So anyway, then I usually put a date down that will become out of date oftentimes. Then you put you can have a list of authors. Notice that this begins a list. You put the name, email, homepage, and you can either have put some of those to be the empty list or whatever if you need. Headline, though, is the one thing you do need. So this line here has to be something. Otherwise, it will, when you try to load it, it will give you an error, and it'll say no headline given or something like that. And it needs to be short. This is supposed to be in a list with a bunch of other packages of what will go next to it. So it shouldn't be, I think, in fact, there's a limit of how many characters, and I don't know what that limit is. I don't know if it's 80, 100, or 50, or whatever. The idea is to keep it short. Keywords, this is where this package that you do, once it gets installed with Macaulay 2, will go into all those lists of packages, which one or ones it will go in. So this one, you might want to say algebraic geometry here, or commutative algebra, or combinatorics, or whatever. Debugging mode has to do with whether if someone has a problem when they're loading not loading it, but using your package, and they get an error. When you get an error, oftentimes you're placed into the debugger. But if you have debugging mode gets false, they'll just get the error at top level. And if they have it, they can set it to run debuggers and stuff like that. But it will treat your package as okay. That's not where the problem is. It'll be above that probably in their calls. Oops, sorry. But while you're actually writing it, you should probably set debugging mode to true. Okay. So anyway, this is the header. There's a couple other things which we'll explain that you should put in here. This is a simple example. And then you have an export list. This is a list, that's the curly braces here, of a bunch of strings. They have to be strings, and those are going to be the symbols that you're exporting from this. Like first function is going to be this. And again, I wouldn't do this typical value get string. I think I mentioned that, but we'll try an example of this. But you would write just method, and then first function of z : string gets this. And then that would be your important function, and you would export it. Okay. And if some packages only export very few things. When you're debugging a package, you can get all the other symbols inside of it by using the debug keyword of your package name, so that you can actually do things like test all the unexported things. Okay. Then there's the begin documentation. This is an open paren, close paren. It's a function call, really, in some ways, and it's telling the system, okay, you're done giving me code. You're starting to give me documentation. This used to be really important because a while ago, and not even that long ago, to load all these things would take significant amount of time. And so what would happen is it would only read to this point, and then only when you wanted the documentation of it would it go on. Now it still does things like that, but hopefully it's transparent. Then you have these doc nodes, okay? You're going to have two important ones here. I don't like this way of doing it. This makes one huge doc node of all the documentation. So I like to have one doc node per thing. If only because when you make a mistake, it's easier to figure out where the mistake is. So in fact, I would recommend not doing these nodes. And we'll go back over and do this in a slightly different way. Okay. Then you have tests. Tests are really important. You have a bunch of these tests, and you assert means that you have something that you're running inside of here, and it better come out to be true. And if it's not true, it will tell you when it will run when it runs all the tests, it will do that. Then you have, as I think I mentioned before, you have the word n. Macaulay 2 stops reading at that point. And then you have, I usually put minus minus, and so that you can easily find it. And then you can put your example that you're working on down below, or anything like that, or any code that you like to F11 so you don't have to keep doing it over and over. But before you submit it for publication or for including Macaulay 2, you want to clean this up. Having a couple statements there about how to run it is fine, but not any of your dirty laundry, basically. Any examples that you're working on currently would be not. You can also do package template, which will, if I give it, like here's print package template of wonderful modules. And then here's what you get for that. This one you get you get two different doc nodes. That's good. That's the way I would prefer to do it. But it doesn't tell you what each of these things are or what the structure of this is, which we will discuss in a bit. Okay. Also, the one thing that this does do that I really don't necessarily like, it has lots of the weird headings for documentation that you almost never use. Okay, so you want to do that. Here's test, and then here is a typical development session. Restart is always a good one to start on. Debug needs package of that. That actually will give you not just the export symbols, but all the other symbols that have been defined in the package. In other words, you can call those functions. You might not want to do it all the time. You might want to just do needs package. Check will run all the examples. Uninstall package is something that if you've installed the package, this is what this install package does, is it runs all the examples in the documentation, creates all the HTML files, and then you can do view help of it after that, and it will give it to you locally on this machine. Okay. But if you're doing this, sometimes you have to do uninstall package. Otherwise, it might, especially if you're not in the same directory, it might when you do a needs package, it might grab the installed version, not the one you're working on. That would not be good. Okay. So let's go back and try this. What I want to do is I want to see if I can grab this all this code and see if it actually works. Whoops. I'm going to grab it to here. Copy it. And now we're going to go to Emacs. And now I'll do this in week 11 example packages.m2. Okay, I'm going to put this in here. Oops, I actually needed to call it something else. Now, I have no idea if these quotes are correct or not at the moment. But we're going to try it. I'm going to get rid of this line. I don't think we need that so much. Here we have all of these things, which we'll leave for the moment. What I'm going to do now is actually I'm going to put this into a file called, what's the name of this package? First package. I'm going to call it our first package. Okay. And I'm going to change the date to be 2025. What is it? April 7th, version 0.1. Okay. We'll leave that. The author's fine. Example, Macaulay 2 package. And document. Actually, I really think that this is an important thing in algebraic geometry. Okay. Oops. I don't know how it does that. We're going to put this to true so we can actually try it. We are going to export first function. I'm going to get rid of this. And here is the line. I can't really see this, so I'm going to put it like here. Okay. Now here I'm going to get rid of this node, and that's going to be slash slash slash. I'm going to get rid of a few things that I don't think are important for now. Subnodes. Actually, there is one other one that is important, but we'll get to. And now I'm going to do another doc here. Okay. And this one is missing a very important one. C also. Okay, we'll put that in. And then here's a test and then an end. And now what I'm going to do, oops, I meant to write that in. What was it, the package called? Our first package .m2. Okay. So I've done that, and now I'm going to do a restart here, and I'm going to do needs package of our first package. And now, what do you think? Is it going to work? No, something just happened. Our first package, what happened? Okay, well, it's telling us mutable unset symbols in our package, our first package. First package. Wait, are we come back here and let's search for first package.
Under key.
Okay, so there we forgot to change that. That's not good. So we're going to put is our first package. And you have a headline here as well that's necessary. Okay, we'll talk about the doc format, but basically it's a string. Slash 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 starts a string, and that's so you can put double quotes inside of this whole thing. Okay. And doc is a function that takes a string and then creates a documentation node for it. And then when you run the install package or whatever, it knows about those things and then can do stuff. So here, let's.
What's a node?
Yeah, so each node you can think of as a documentation node is like a single HTML page. Okay. And so here, that one is going to, the key that you would get at it from Macaulay 2 is if I do help our first package, it will give me that. It's not necessarily HTML. It can give it documentation in text format when you're in the system as well. We'll talk about that. This is this though is space sensitive like Python. Okay, Macaulay 2 in general is not, but here it is. I tend to indent 4 times, not two or 1 that was here. See, this is indented by 1. So I'm going to actually, we'll do a 2 indentation here. That's another one. This one will be indented 2 further. This one will be at the same spot. And some of those were actually correct. Maybe they were all correct, but the trouble is when you go from cut and pasting it, any tabs that are in there are just messed up. So so there's that. Here, I'm going to put this over here. So these are all indented at this level. So this is our documentation. Caveat, still trying to figure this out. Use this function to screw up your system. No, it will not really screw up. Yeah, okay, so what there is, each documentation node has a key or several keys. It has a headline. This is what will get displayed with it whenever it's showing that package. There is that other headline. Why they're both of them, it's a little unclear, but at any rate. And then description. Description can have text and it can also have Macaulay 2 examples. So I can do an example here, and then I can run first function of 3. Okay. No, let's do 3. And then there are no caveats. You could also have C alsos. And here, it will already give us a documentation, but what we can do is we can do it to first function. Okay. Well, we can also do it to first function. First function is a method, so that would work first function. But I can also, since I have a method here, I can go directly to that here, first function of ZZ. In this case, it won't matter because if you look down here, the documentation has both the node for the specific method where you call ZZ and the function. We're going to put in another version of it. First function of a string, say, and this will return a string, and it will give us a string. A string will it gives us a string, and then we're just going to double it up. Stir, okay, and return that. Then we're okay. So now what we're going to do is so we've got these two documentation nodes. See also, I don't know what we should see also here, since we only have one function name. And a test is this. Okay, so let's actually try this. I'm going to restart, and we'll needs package. It loaded. Okay. Another time it won't load is if, suppose in my function, I have I do let's set a local variable m to be 13. Okay. We're not using it, but let's suppose that we have one in there. Now I come down here and I do needs package, and it worked. Yeah.
What's the thing that you're doing to like sort of like finalize the package, and then when you restart your needs packaging it?
Actually, wait, something went wrong. Why did this? Sorry, just a second. Why did it not? What directory am I in? Is that where I am here? Oh, maybe I didn't save the file. Maybe I didn't. Yeah. Okay. Good. Sorry. What were you saying?
What are you doing like after you're done with editing the file, and then you want to turn it into an actual package? So you do something to it, and then you say restart needs package and to check.
Yeah. If I do restart and I do needs package, and it gives me this error. Okay.
No, I mean
No.
like before you even hit restart. What's the thing that you're doing to make it an actual package?
Oh, it's in a file, which it matches exactly the name of the package.
So you're
dot
hitting
M2.
save?
I'm hitting save in here.
Okay.
Sorry, Control X, Control S is what I'm hitting in Emacs. Yes,
May I ask a dumb question?
sure, of course.
How are you clearing with mine?
Oh, so let's see. To go up in Emacs, you can do Control P. Down is Control N for previous and next. If I want to clear one, I can do Control K and it wipes it out. If I don't, I can do Control Y to put it back, and stuff like that. Yeah, I mean, I'm sorry. It's just so second nature. I don't even. I have to actually figure out what key it is by actually doing it. But so. All systems have these kinds of things. Some of them are better than others. Vim is actually very good at this kind of thing too. Vim has its Emacs versus Vim is an interesting flame war kind of thing, but VS Code can do a nice job too. I actually have it set up in VS Code to use Emacs bindings. Yep.
Question.
Yes.
There's not two Macaulay 2 extensions. Yes. Someone published another. I was just checking.
Who did that? Is it Doug?
No.
Corey Harris had the first
Yeah,
one.
this is fun.
Yeah.
Sure,
I have no idea.
it's got 22 downloads.
It was published like
Loser.
2 weeks ago.
I have no idea who that is.
I don't know, but just trying to download, so you should not worry about it.
It has code completion with IntelliSense.
Enriching AI with it.
Anyway, at the end of May, we have a few people coming here, and we've been working on the Jupyter and VS Code interfaces, and they're getting better. The Jupyter one is actually getting quite good at this point, and the VS Code one is sort of passable, but needs work yet. Okay. Okay, so anyway, so I'm just so basically, if you do the example, I mean, you can just do this. I would never just type this in. I would, the other way of doing it is to have I could do package template. of our first package. In Macaulay 2, I do that, and then it displays it out. And then what I would, maybe I would print it, and then I would actually copy this and put it in a file, and then start with that. So those are the two ways I do it. I oftentimes use that rather than starting from this one. But if you haven't done it before, it's good to start with one that actually has code in it.
Was there a thing you did right at the beginning where you set the file path?
Oh, so in Emacs, when you're running Macaulay 2, you hit F11, F12 to start Macaulay 2, right? And you can also do this in Jupyter. You have to do it in a certain way. Wherever Macaulay 2 starts up is its current directory. You can always tell what it is inside of Macaulay 2 by doing run pwd like this. And in mine, it's in users, mic, source, cocag, problems, okay? And that's the directory that this thing is in. And then when you're in there, if you just do needs package of it, it will look for it because it's on your path. That's the easiest thing to do. You can also change the path. You could do path. Here's the path where it looks for things. Some of these are placed in by my init file, and some are just in because of the system. So here are the ones in because of the system. This is where the init file stuff sits. Oops, let me actually netlist this list. So here are the ones. So I have this, this is some project I was working on. Here's another project I'm working on. I tend to put those in my initialization list so I don't have to worry about where I am. The current directory it'll always take stuff from. These two things are if you do this is where your init file will go. And on a Mac, it's in this weird directory, which is in your user directory, library application support. It's actually hard to find because they hide it, which is very annoying. But it's also hidden on Linux or Windows systems because it's called .Macaulay 2, and the dot also hides it. So your call whether which way you like. Any case, on the Mac, this is what's happened, and then this is where all the Macaulay 2 code is on the version of Macaulay 2 I'm using. And here's another piece of code, which sometimes the path gets changed on the front, sometimes on the back. That's not very consistent. So any rate, so that's how you would deal with that. So yes, so the way you do it is you have to do path equals. If I do append path comma something, it will not change the path. Path is just a list. You cannot change it unless you assign to it. So path equals, I could do append of path, comma, A/B/C/ or something like that, that won't find anything like that. But I can do something like that. And if I do that and I do net list of path, it comes out like this. It might be that you need that final slash in here. Now notice how all those did, but not the one I put in. I'm not sure about that. You'd have to check. Okay.
You know what I'm saying? Like how?
All the way to the beginning. So you could go all the way to the beginning, like here. That's from the root. You can tilde is your home directory, and then that's what typically you do. Dot is your current directory, which will change depending where you are. So so in this case, I'm just doing it in the home directory. I wouldn't need all this other stuff in there. You do have to be careful though. If you have a name of a package in here that matches one of the Macaulay 2 names in here, it will use that instead of this one when it loads. That is not cool. And it's I'm trying to figure out, we're trying to figure out maybe ways of really fixing that. But there are times when you do want to replace it when you're working on it and stuff. So it's a little tricky. In any case, so here's our new package, and this is it. I mean, it's almost all on here. Let's actually try running. Oh yeah, we have to get rid of that problem. M equals 13 we didn't want. So I do Control A to get the beginning line, Control K again, and then I save it with Control X, Control S. If I don't notice I don't have all the the menu, and little icon things here. Because I disable them on mine. Because I just use the command keys. Although there are some things up here that give you some stuff for Emacs. Any case, let's go back down here and try this again. Needs package, and so it needs package. Now let's just try it here. Let's do first function of 2, and it gives me something. Okay. How about first function of high? It gives me high. Okay, remember it doubled it on it, so that was okay. Now that's maybe not what I want to do. Maybe I want to install the package. What I recommend for installing packages is the following. So this is what I'm going to be doing. I'm going to do a restart and install a package. But before that, I'm going to uninstall it just in case. So I'm going to do uninstall package and then the same thing. Okay. I uninstall it and now I install it. Okay. It actually takes a little bit of time because what it's really doing is it's running through all the documentation from Macaulay 2 also to sort of do it, which is a little annoying. But anyway, so here is our first package. It's been installed. It did examples for 2 different things. And now let's do view help. Well, here, let me put it over here. First of all, I can do help of our first package. Our FRAT package, our first package. I can put quotes around it, but in this case, I think I don't have to. And it comes over here and it displays it in some sort of textual version of the HTML page or the documentation page. See here, it gave us, we had an example in there. Here's how we had a C also in there. And then we also had our author and version information. Here's where it can actually click. It tells you here where the package, where it is. You can't actually click on it and get to it. And then here's the list of all the things you export. Functions and commands, methods, and so on, okay? And for the programmer, what is our first package? It's an object, which is a package, which is a type in Macaulay 2. It's a type defined at top level. But anyway. Now we can also do, probably that's less useful. You typically would do view help, our first package. And this is what you see. Let me make it larger. Okay. It's, first package is a basic package to be used as an example. We wrote this stuff, or we took what was there. And then we also put the C also in, and the author is there. And then version source code, we can actually, if we want to look at it online, you can always do that. You can go to it and actually see it where it is. But that's not going to be necessarily your own version. Notice where it is here. Application support, Macaulay 2, local share Macaulay 2. This is the installed version of it that it's getting. Okay, so in other words, if you go to that location and try to change it, that will be bad. You want to change it in your actual code that you're working on. Okay, but nonetheless, the point of a package is pretty straightforward setup. Okay, just these 5 different sections. Okay, and this is what it looks like. And if I don't have any documentation for first function of string, but if I go to first function of CZ, this is what I get. Well, it's actually first function also. And ways to use it is first function is easy. You click on it, but this is already the node for it. It should say, why doesn't it say, oh, that's this method. It's not the, so here, this is one thing I could do. I could also make another node for it. But anyway, let's not worry about that for now. Let's come back here and take a look at it. Okay. We also can, another thing we can do is we can check the package. Our first package. Okay, and this is, let's do a guess and restart. I kind of like to do restart. Some people are very much against them, and you can do whichever you prefer. But I like, if sometimes people will just load parts of it and think, but then you don't always know what your state is. And you might have gotten it into a weird state if you only load some of the code and things like that. Okay, so I check it and it did not know what to do. Why not?
Oh,
I did restart and then I did check of our first package and it couldn't do it. It doesn't know what it's supposed to run the test. Yeah, I did. Here's a test right here. The trouble is that this is a symbol and we haven't loaded it or anything like that. So since we haven't loaded it, it's just saying look at this. No method found for applying check to our first package of class symbol. It's not, like a package or something else. So what we have two ways around that. One way is we can make this into a string and then it goes and finds the package. So if we do that, it runs it. Warning symbol, oops, what is it? Is shadowed. Oh, our first package is shadowed because we used it here, but now we're redefining it here. So this version is gone. So it warns us that that version, that string, if you want it, you could get it using a synonym. It's sort of bad actually. But at any rate,
That's why it is good restarting.
yeah, restart and then check it, and it just says capturing and does the check. Now, if the check is wrong, assert that that is equal to 3, for instance. Here, let me not change that. Let me put another one in. How about assertion of 1 is equal to that? Okay, pretty sure that's false. If I run it, that assertion failed. Okay, now I save the file. I come here, I do restart, I check it, and sure enough, I got an error. And I think we did this last time. There's this huge, awful name of a function in here. And it says Macaulay 2 exited with status okay. So I click on it and you come here and it shows you where it failed. In VS Code, it will click on it too. I don't know how to get that behavior in Jupyter at all. Okay, so so at any rate, so if you're doing it on one of these systems, it works. Okay. Figure out where, it will give you an error, but it tells you where that error is. And if you click on that in here, like in the M2 window, here, see this is a file name here, and then a line number, and this is actually where this is the file and the location of where the error is. And when I click on it, that actually gives me the actual file that was causing the problem. And here gives me the output of what caused the problem. So you can go back and check at it. What? This does not go to the source. This goes to a place where it put to get to the actual source of where that is. Yeah, that's a good question. You would like that. This particular case, it's not giving that to you. So you'd have to figure out where this is. Actually, that's a good question. In tests, it tells you where it is, but in examples, it's not.
Do you just want?
Sorry, the other way around.
What
Ye-
behavior?
What I wanted, oftentimes, if I have an example with lots of things and it errors, I want to know what the error is. So I click on it, I see what it is, and then I go back to the source code and fix it. But maybe I would like it to go to the source code, but it doesn't know where the source code is, because at that point, it's just loading it from an installed version. Okay. Yep.
did you have to load or install the package before hitting check package?
If it's a string, not. But what we can do, oops, let me go to our first package. I can also do the following. Here, let me change this. I can do needs package of our first package. Okay. It loaded it. Now the question is, which one did it load, by the way? I can do peek of loaded files. Loaded files is just a list, a mutable list of all the files that have been loaded. It's going to be a little overwhelming. So I click on it. And here, look, it loaded the one that we want. If it said something about share Macaulay 2, or something like that, then you knew it was loading one from somewhere else. This is actually a really good way once you've been doing this a lot to get to the right behavior. Because sometimes you might have installed it or you might have an old version of it and it's grabbing that, and this way you can take a look. Then but once it's loaded, what you can do is now you can just check it. Another one you could say is, check 0 failed. So how do I see that? If I do tests, I think it's tests of 0, our first package, like this. And now it does give me the location of it. Test input, and see this? If I click on it, it will take me right to the file I'm working on, okay? Or where that got loaded. So that's and so you can actually see the example, go right to it and use it. So it's kind of it's not something you actually need until you've been doing it a while, and then it's kind of nice to be able to do that. But as far as the first package goes, we've got it now. Let's talk about the structure of a documentation node, though. That we have not really done yet. There is documentation for it. Right where we saw creating a package, you can go and click around and take a look. There's 2 documentation nodes we have here. The one is for the package. You always need that one. It will complain if you don't have it. The other one is for any function. So for instance, I could change this. I could put function first, and then what we'll do is it will look, that will be the name of the node. I could also put the other one in here. Well, here, let's not do that now, okay? What does a documentation node have in it? At the same heading out here, there's a number of things. Key is necessary. You have to have at least one key, but you'll have you could have a number of them. What this means is that it will also, if you try to go to the documentation for this, it will just take you to this node. Headline is going to be a small thing that will get displayed in lists and things like that. Usage is just a free-form thing, how you want to use it. You could say other stuff in here. You could even have several lines of usage if you have different ways of doing it. Inputs, this is N, and actually what I could do is I could put the type afterwards, N:ZZ. Okay, again, I like these being indented the same amount. That's 2N. I like 2N here, 2 in here, 2 in here, 2 in here. Outputs. You don't have to put this colon in here, but you could say colon returns a string, okay? You could even do S equals this, and then do S:string. And now this one has to be indented. So for each one of these things, you have to say, you can say something about what it is. Notice that, look at this, you can do /TT, you can do basic things. Here, what we could do, for instance, is we can say, I could do this. N is an integer, actually, of the form e raised to the, pi I or something, /pi I or something like that. Okay, that's not correct at all, but let's actually see if this works. I go down to restart. It needs package did work. Now I'm going to do restart, uninstall package, restart, and now I'm going to install package and see if it runs those examples. It did. And now I'm going to do view help of it. Okay. And now I'm going to go to first function of this. And yeah, N is an integer of the form e to the pi I. Okay. So you can do it. It uses Kotek actually, but sometimes it uses MathJax. Kotek, I believe, is used in VS Code and Macaulay too. And MathJax is used in Jupyter. But for this kind of output, it's all the same. It's all just Kotek. They're supposed to be compatible, but they're not complete. Which one? Kotek is supposed to be faster, but MathJax, I think, does more stuff. It allows things that Kotek doesn't allow. some
Divergence.
divergences, yes, which is a little annoying. It's a lot annoying, actually, but at any rate. Okay, so this is, are there any other questions about documentation?
Yeah, like,
Oh, wait, we're still on
a
that.
separate. You put the documentation for a method in a separate place in the actual code.
So So what you do here is, what we have here is the name of the function or the method plus the actual function that we're documenting. Okay? We could do those in two different documentation nodes if it were handy, but a lot of times your function does one thing and having it all in one place is good. Oh, that was up here. That was at the beginning of the file. It's in the same file. No, not in Python. You don't do this with a quote, double quote, or triple quote or whatever it is. No, we decided that that was too much stuff. I mean, there's some advantage to that, but we don't allow it. It's too much. I mean, the length of this thing is typically kind of overwhelming for it, so it's kept separate. Yep.
How sensitive is the documentation node stuff to format? Because
Very sensitive.
very sensitive. Okay.
Okay, so what is sensitive about it? Let's get this. All of these main headings, key, headline, usage, inputs, outputs, description, and see also have to be at the same. There is no see also yet, but we could put see also first function. Actually, let's just do, I think really it's really important to have the notion of the Jacobian of a matrix here. And we'll see if it actually finds it here, because that's in Macaulay 2 itself, not in this package. So if I just put it here, I'm a little unclear actually whether it'll take it or if we have to put Macaulay 2 : this thing. Yes.
Do you have to scope name with the package, or is it just sort of flat?
It's in a dictionary for the package. If you create any functions, and the export list actually will make it into a global value in your session.
So what if I have flashes?
Then it will tell you what to do. You can get at the different ones by like package name, $, the actual name. Typically, better is to try to avoid that. But there are times when you can't. So you would do that. It tends to tell you what to do in that kind of case. Anyway, so all of these have to be at the same heading. Let's actually try this again and see if that Jacobian worked. So if I come down here, I can do, where is my install package? I'm going to uninstall it, and then I'm going to install it again. And let's take a look. It did it, and now I can view help it. And now I come here and let's go look at the code for that. Yep, the Jacobian. Does it find it? It did. It went to the Macaulay 2 doc that is in the system. Okay, so anyway, so I guess you can just do that direct. But if you sometimes you have to say what package it's into. Yes.
For some reason, it doesn't like the documentation that I'm doing. The documentation nodes. How do I, yeah.
Okay, so let's actually take a look. Suppose that I accidentally put the C also in by, actually, let's do it one less, okay? So it doesn't look like that different, but that's 2 and that's 1. Okay, let's actually try running this. So I'm going to uninstall the package. I'm going to restart, uninstall, restart, install. A little surprised about that. Let's see what it did. That was in here. Wait, which one did we do that to?
The one with the Jacobian.
That's weird. It took it. Well, if I put it in by 1, let's see what happens. Okay, actually, these are in. I gotta make it 2 in here. text and example are typically what you have here. And the C also would go out. But suppose you mess it up and put the C also here. Okay? Let's see what happens then. I come to restart. Oops. I uninstall the package, restart, and now I install it again. Oh, and it came out with an error. Unrecognized keyword on line 61, C also. Expected, and then it gave you the various things that were allowed in that situation. Okay? Typically, you don't need any of those. There's a lot of different possibilities. Example and text are the only two that you tend to use. Pre and canned example are sometimes used. Code, I don't even know what code is. And tree is not relevant for now. Okay, so that's for organizing the tree of all documentation. What? Pre is like a pre-element in HTML. So if you want some piece of code that you don't like, suppose I have a piece of code that runs forever. Yeah, not forever, but it takes a long time to run. If I put it in as an example in there, it will try to run it, and it will be bad. Okay, it will sit there until it finishes, and so it might take. Suppose it takes 20 minutes to compute that example. You might not want that, but you might want to have the code around for someone to actually be able, or yourself to remember what you did to get that. When you really want it. So you would do pre instead of example. It would just put it in, and then it would just display that example without output. Or you could put the output in for that as well, and it would put it all there. So that's sort of the kind of thing. But actually, now we had a problem here. This C also didn't understand. So if I put it in by 1, I think it will also not understand it because it will think it's part of description, and C also is not one of the keys that is allowed there. Text and example is. But I guess if it's outside of it, it somehow is somehow seeing it, which is a little surprising to me. So anyway, so here the typical thing you could do is you could have lots of these sort of things. I could say text. This function is also used in our proof of the Riemann hypothesis. Okay, and then we could do an example. Zeta is equal to a method, and zeta of x, zeta of an integer, maybe it always returns 0. So x gets 0, and then we could do first function. No, I don't know. But anyway, so we could do something like this in here. And if I do that, we don't need that there. This takes as input x, returns 0, and we could call zeta of 3. Okay, and then if we come down here and run it again, restart, uninstall, restart, install package. Oops, it gave an error. Shoot, what was our error? First, wait, what is our error? Actually, let's go to this one. Oh, zeta is already defined. So I'm trying to define zeta again. So rats. I guess we'll have to give up on our proof of the Riemann hypothesis. Okay, so at any rate,
That's because Zeta was already.
exactly, exact. Whoops. So let's go back to our package.
So that,
No, I think the trouble is that if it's actually defined in the system or in a package that you are importing, then those are treated as read-only objects, and you cannot change it. So it would be hard to change zeta, sadly. So we'd better get rid of that here. Where is it? Oh yeah, here it is. How about zeta? Okay, And so if we have that, it would do it. Now, the thing here, the main thing in documentation are these text notes. You can also do where n is equal to like sum of sub I equals 1 to 5 of I or something like that. So we can put stuff like that in, and then but you have text section, example section, text example. That's the main thing. That's typically what you write. You make sure you indent all those the same amount here, and then roughly the same amount here. Okay. It might be that you could get by with a little less, but that's how that works. And this is, and then for this, the main documentation, if you were writing a package for use by other people, you actually would really like to say something about why it is there. You might have references. The geometric decomposability package that we looked at last time of Mike's is a good example. It has a bunch of references. That's really good to put in. And then yeah, so this is a good thing. Now, what I have suggested for you for a thing to do is to write your own, essentially redo this. But now I want you to write in a function that will take in a ring and then create some specific ideal in that ring. And I can give you an example of what I would, what might try to do, but then you have to figure out how to write that. And typically, rings and packages are tricky because if you have a ring in Macaulay 2 and you assign it to something, you also get all the variables as things. And in packages aren't allowed to define things with one character. Because that would make it, you can't export a thing with one character, because what will that do? That will make it, anyone that uses it, that one character thing will be read only. That is typically a really annoying thing. So we don't allow that. So instead, you have to, there are a couple ways around that, which we can discuss. But I think that was actually longer for doing that than I'd planned. But so first of all, are there any questions? Yes.
So in the check, if it says capturing check 0 practicing packages or whatever it's called, that's good. That means it succeeded.
But it will give you an error if it didn't. But sometimes it will say, oops, retrying, and then it does not a capturing anymore. It does a running example. And capturing means it's running in the same process. And running means it's starting up a new Macaulay 2 and running it. That's what we always did, but that takes a little bit of time for each one. When you're doing hundreds of these things or thousands of them, then it can actually take quite a lot of time. For packages here, it's probably not a big deal one way or the other. But if you see both of those names, that's what it's doing. Other comments or things like that? But I think, as I said last time, writing a package, first of all, for anything that you're working on that will be useful to others is awesome, because then you can actually write a paper on it then too, for JSAG, and get a little gold star on it. Plus, you get a paper out of it, and that's if it's something that is an algorithm that you've done or some features that you have put in. Even if you didn't do the math behind it, it can still go in. But it has to be something a little larger. It can't be just a little single diddly function. That won't certainly make it. But it's also good, is having the paper for the package, and then having the package and the documentation and the tests. It just makes it so that it will be kept up to date in all Macaulay 2s as it goes. And for your own code, it's great. Suppose you're working on a project, you write a little thing with some of the code for it. You have some documentation to remind yourself what it did. You have it doesn't have to be amazing, but just having something. You have a couple tests on basic stuff. Then when you get busy, you're not working on it. Your co-authors are deadbeats. So you finally get back to it after about a year and you try it again and all of a sudden normally nothing will work. And then you can try these tests and you say, oh yeah, I had screwed up and forgot to change something or maybe something Macaulay 2 changed or something like that. So it's really a good way to get back up to speed fast on a project. And yeah, when I don't do that, it's very sad. And I don't do it enough that it's sad. But I also do it on a lot of projects, so it's good. Can I demo the debugger? Yes. Maybe I'll do that next class when we're doing the project, so I can spend a little time on that. The debugger is mostly is best used when you load files like a package. If you try typing in by F11 a function, the debugger won't get started on it. Actually, I could probably show it now. Is it worth it, or should we? Maybe now it's getting to. We should take a little break, and we'll figure out what to do after that. So we'll come back here and let's do 10 minutes, and then we'll figure out if we're gonna. I'm probably having you do the package thing while it's fresh is not a bad idea. But if you've already done package stuff, then you can take a look at some of the other problems on the list. One is we can sit and do some package stuff, but maybe we should do a little math first and then do that. So the math we could do is really finish the primary decomposition with the get the whole sort of structure of it up, which is actually pretty good, and we need to do that. But maybe it's good to take a little break and do the Eisenbud-Hunicke-Vasconcelos method for getting associated primes.
Are we going to be able to do them both today?
No. Well, maybe if we, but they're going to take a little bit. Actually, this might not be too bad. Where's my, wait, I thought I had 1, 2, 3. I thought this was 4 pages.
Turn on the light.
Yes. No, I can't, but someone else can.
Blackboard by 12.
Oh, yeah.
There we go.
Are they all on? Okay.
There we go.
Amazing.
Okay. So what I would like to do is go through a very cool relationship between Ext and associated primes. So here's our situation. So this is the EHV. So this is a paper. Oh man, when was the paper? It was pretty early, in the early 90s, basically. It's Eisenbud, Hunicke, and Vasconcelos, and it's just pretty cool. So let's talk about our. So here's our situation. So R is going to be equal to K of x1 xn. Or a localization of this. Actually, let's not. We're interested in localizations of this. Okay. So let's just recall. Okay, so this is about localization. So let's we can do it for any multiplicative set, but suppose I take P is contained in R is a prime ideal. And the idea is we want to invert all elements in R, but not in P. Okay. And so how do you do that? Let's so RP. We could do it for any, we don't have to do it for these particular multiplicative sets, but this is, if you don't know about it, then don't worry about it. And if you do, you know what's going on. Yep.
I'm just Googling the paper, Conventiones, 1992.
Yeah, that sounds right. Okay, so this is just the set of F over G's, where F and G are in R. But G is in this set. G is not in P. So it's not 0 in particular. Okay, modulo an equivalence where F1 over G1 is equivalent to F2 over G2. If what holds? Well, it depends on what our ring is. If R is just this, it's a simpler situation. Otherwise, it's more complicated. Certainly, we want these to be the same fraction if F1 G2 minus G1 F2 is equal to 0. Okay, that will certainly be the case that we will want these two fractions to be the same. But there might be other cases that we want them to be the same, because suppose I take a unit and I multiply that unit here. I want it to be the same thing. So in fact, it's really u times this is equal to 0. If that is equal to 0 for some u not in P. Okay. Now, if it's just R, that won't happen because it's a domain. But if I have a different ring, or R mod I or ... But we're going to mostly be working in this ring here. So we don't need that u. Anyway, that's our localization. And so so what we have is RP is a local ring. Remember what that means? It has one maximal ideal, and that maximal ideal with maximal ideal P RP. Okay, so we just take P and extend it out. Basically, we have the map R going to RP, which sends 1 to 1 over 1. In the cases that we're considering, this is an inclusion. If we mod out by an ideal I, we might get things that go to 0. So then if I take this PRP is just take the same ideal in here generated by the original guys. Okay. Here's one interesting problem which we do not have a good solution to. So given an ideal I contained in R and that we have this P, compute I times, we extend it up to IRP. So this is an ideal in RP, just generated by the same elements as that. And now contracted back to R. If one could compute this, it would give you primary decompositions quite easily. Actually, it's essentially equivalent, except that for primary decompositions, we can get all of them. But if I only want one of them, I don't know how to do it without doing a primary decomposition. Okay, so that's an interesting this is a sort of open problem. If I give you a prime ideal P and I give you an ideal I, how can I get this without doing a primary decomposition totally?
Are you saying this is still open, or this is a problem this paper solves?
No, this is open. Open meaning we know a computation for it, but it's a fairly hefty computation. So open, one do it without a full primary decomposition. Okay.
And you just take the ideal and then compute its saturation.
Yeah, if I give you I and P, can I just compute the saturation without any extra effort? I mean, here's one. If this P, if I take instead of inverting by the complement of an ideal, I invert by all powers of an F, then I can do this. I can compute it via the saturation. But for a prime ideal, just don't really know how. But anyway, this is not what we're going to do right here. But I felt like it's an open problem that would be nice if it had a solution. So I'm surprised also. Okay, so what are key facts about this stuff? I guess what I might normally do is, if I let S equal R minus P, and then I think of S inverse of R is another notation for RP, right? This is the standard way of doing it in like at Team McDonald and so on. S inverse though is a functor. It can take not just R or free modules, but maps to them and also any modules. So S inverse is a functor. And if you really want, basically S inverse of M is denoted MP. And really what this is M, this is if M is a module, sorry, an R module. This is just M tensor over R, RP. Usually this notion means extend scalars from R to RP. So that's exactly what that is doing. So you can do this for modules and everything. And the key fact, first one, is that this S inverse is an exact function. I.e. takes exact sequences to exact sequence. Okay. So as an example, this is sort of an example. So R mod I, that's a module, and I can localize it. That's the same thing as RP modulo IP, which is I times RP. Okay. And really that's coming about because I'll do the order this way for the moment. If I do this and I apply the localization functor, what do I get? I get IP here, which is I times RP. I get RP here, and I get R mod I localized. And since that's exact, this thing is equal to the quotient of that. Okay, so basically, anything you do homologically is just completely compatible with localization. That is probably one of the best reasons for considering these things. This is you don't need exact sequences to do this one. It's just a case. Another example would be a free resolution. So let's take I is equal to the rational quartic curve, which we've done before in R, which is in 4 variables, K of A, B, C, D. I'm not going to worry about exactly what it looks like, but what is the resolution? It's R mod I. R, there's 4 generators of it, 1 quadratic and 3 cubic generators that we've seen here and there. There were 4 linear syzygies. So this is a 4x4 matrix of linear elements. And then there was one more guy here. And if you do the order right, it has 1 column and 4 rows, and it's going to be A, B, C, D. Okay. And then this is just the polynomials F1, F2, F3, and F4. Okay, and these are linear. Okay, now, what if I now take this and I localize at any prime ideal P? What happens? Kind of interesting case. So now localize at some prime at P. Well, I get a free resolution of R mod I localized to P, because this thing is exact after localizing. And each of these things are going to be RPs to some power. Those are free modules. So so those are all, so this is going to be localized to P, and we get a free resolution of R mod I localized at P. Okay. And we could do this for any module whatsoever. But now what does that mean? Let's take as an example in here. Let's take the case. So e.g., suppose the variable A is not in P. Okay. So we've localized, maybe on the problems sheet, I give you a couple things to play around with this. Like, so a couple different primes that get mentioned. It's on the last one. So this is in fact, the rational coordinate here. P could be ABC would be one of the ideals, or ABD. Actually, the ABC, that ideal D is not in the prime ideal. So, but anyway, suppose A is not in from this one. What does that tell you? Well, if A is not in it, that means A is a unit. So therefore, A in RP, okay, the image of A in here, which is A over 1, right, is a unit. Because 1 over A is just well defined. So A is a unit. That means that this last syzygy is saying that a unit times the first guy is equal to a combination of the other 3 guys. So therefore, this is not what's called a minimal resolution. So remember what a minimal resolution is. For free, I don't know if we actually did that, but in the local case, recall a minimal free resolution over say RP is a free resolution such that every entry of every matrix is not a unit. So this is not minimal. Yep. Actually, to tell you the truth, it doesn't even have to be containing I. It could be any prime ideal. But if it doesn't contain I of R, sorry, P is a prime ideal, P containing R, a prime. Okay. However, if P is not if ideal I is not contained in there, then all of a sudden when you look, then I will have units in it, and so it will be the unit ideal up above. So then you're getting a free resolution of the unit ideal. Still exact, but you know, yep.
Okay, sorry, that answered my question. I was gonna say, are we allowed to there, but I guess it's exact.
It's exact. It's not particularly minimal then, because yeah, it's just not minimal at all. But in that case, but here, if A is to tell you the truth, if P is a prime ideal that doesn't include any variables in it, then any one of those things is a unit. And so we can prune this resolution. That's telling us that we don't need one of those syzygies there. Okay. So anyway, so we can prune. Let's give this a name. We'll call it star. To get a smaller resolution. To get a minimal resolution. Of R mod I localized at P. So how is it going to, what happens when we do that? What is it going to be? I.e. in this case, we have R mod I localized at P. We have R localized at P. R4 localized at P. Okay. And now what do we have here? We have a 4 and a 1. This one we don't need, so we can just ignore it. And that means we can, so that says we don't need the first syzygy, the first column of this thing. So what we get is we can prune it down to this, where this is the same matrix as that without the first column. Okay, does this make sense? So basically, it's linear algebra at this point. You have some stuff, you have units, you can clean it up and make a smaller resolution. This might not be minimal either. There might be a unit in this matrix. This is a matrix of linear things after all. Maybe there's even an A in here. What happens in that case? So suppose A is an entry in this matrix. In here, e.g., let's suppose this is a 4-column by 3-column by 4-row thing, and let's suppose that the last column is A here, and then something here, and then we also have 2 more columns. Okay, so do you all is this understandable, or am I being too vague? I'm just taking this and I get this. That means, what is this syzygy telling us now? This is a syzygy on these 4 polynomials. So that means that polynomial, first one times this, second times that, third one times that is plus A times the last one is equal to 0. Since A is a unit, that means that the last polynomial is not needed. So then what we can do is, if that's the case, we can go to R mod I, P, to RP. We get rid of one of those things. We get down to RP 3 copies here. And now we're down to 2 here. And if we could get rid of another one, we could go to 2, 1, or something like that. So all of these things, though, are pretty nice. They're shorter than that one by 1. And there's just some nice matrix. Actually, there's a theorem that tells you what these things have to look like. But what's the point of this? You start with a free resolution up above, and when I calculate the localization, I can sometimes shrink the resolution, and I can do that pretty nicely. Yeah.
What does your choice of P say about how much you can round the resolution?
It very much depends. So if the different P's that you choose, in fact, we're going to be choosing minimal prime, or we're going to be choosing associated primes of I and seeing what we get. And so, and each one is going to give us something here, but we have to see how that goes. Okay. Okay, so a few facts, more facts, just as a recollection thing, although we didn't really do some of these things. So let's let M be an R module. We will typically be using M is equal to R mod I, but we will also be using it as X I of R mod I into R. Those are the 2 types of modules we're going to be applying this on. But in any case, so here's some definitions, so basic notions, just to make sure we're all back on the same page on this. A, the dimension of M, sort of the Kroll dimension of M. You can define it in a number of ways, but really one way to define this is just say it's the dimension of M mod the annihilator of M, which is not R, this is R mod that. Oftentimes, if you want to know about geometric things, you can replace M by the annihilator and then take a look there. Associated primes are not quite one of those things, but anyway, it's not too far off. So that's the first thing. So just when we talk about dimension of that, we're just talking about dimension of R mod some ideal that corresponds to it. Which makes sense. Up here, this will match the dimension of R mod I as the Kroll dimension, because M, the annihilator of M mod I, is I. Okay. The second thing, there's a notion of associated primes of M. So associated primes. This is, by definition, the set of all P's in R prime ideals, such that, well, what was the way we defined associated primes of R mod I, or of I, rather? It was that we wanted some element that was essentially annihilating it. So this is such that P is equal to the annihilator over R of a little element M for some M in M. Okay, so if I take some element in M, I look at all the elements that kill it, and that gives me an ideal. if of all those ideals, some of them happen to be prime, and the ones that are prime, I call associated. This is exactly matching the definition of associated prime that we did for I, except that that was this. So the associated primes of I that we had defined before from before, that's by definition is just the associated primes over R of the module R mod I. Okay, because the annihilator of it is that the ideal quotient thing. So this is a usual thing in commutative algebra that you actually are interested in the module, but you will oftentimes define the notion to be coming from the module, you know. So it's supposed to make it easier to just deal with ideals and not worry about modules, but then it really confuses you once you actually have both of them in hand. Okay, because what are the if I think of I as a module in a polynomial ring, what's the associated primes of it? There aren't any, right? Because you're in a domain, and R mod I is if I is which one was I just thinking of? If R, yeah, I'm not doing R mod I. I'm taking I itself. What's the annihilator of I in a polynomial ring? It's 0, unless I is the 0 ideal, in which case it's everything. So so that's not a very interesting case. It's just so typically it's overloaded then to mean the associated primes are equal to that. Okay. Facts about this. This set is finite. By the way, we could do a whole primary decomposition thing of these as well, if we wanted to. Minimal elements of this set are the minimal primes of M, and this also matches the minimal primes of the annihilator, which I don't think I'll write down right at the moment. And then the other thing that happens for associated primes is if I look at the set of zero divisors. So that's the set of F in R, such that F times M is equal to 0 for some non-zero element, some M not equal to 0 in M. Okay. So these are the set of zero divisors of M. Okay. This thing is actually equal to the union of all the primes where P is an associated prime. Okay. And this happens also for R mod I, is that it's this union. Okay. The next notion we need, which we have talked a little bit about, A, B, and C, is suppose now that R, comma M is a local ring. Actually, maybe I should say RP comma P is sort of where I'm going here with that. But let's say we have a local ring and M is an R module. Or R is equal to K of x1 to xn or x0 to xn is graded. And M is equal to the set of positively graded. So, and this is the set of variables x1 to xn. So I'll say positively graded, meaning these things have to have positive, it can't be degree 0. Okay. And it's more general than that too. And M is equal to a graded R module.
Or you said M is an ideal?
M is an R module.
No, down below.
This little m, so here we have some R comma M being a local ring. The notation for that means R has one maximal ideal, and that's the maximal ideal. Okay, that's one situation, and we're going to be using that for localizations. But another case that works is if R is this, which is not local, but if it's graded, it's kind of actually it's simpler than local, where you could treat this as the maximal ideal. Okay, And graded modules then are kind of, so the graded case is very similar to the local ring case, but easier typically. Okay. And then we have the following notions. We have the depth of with respect to M of M. Since it's a local ring, we could leave that out, which people do. That this is equal to the maximal length of a regular M sequence in the maximal ideal M. This is we had defined before. Do you recall what this is? So this is you give yourself a bunch of elements in M, in other words, non-units, basically. And then you take a look at M and you keep you take the first one and M modulo that has to it has to equal it has to be a non-zero divisor on that. And then when I mod out by that one, the next one has to be a non-zero divisor on that, and so on and so forth. So that's what a regular M sequence is, and this depth is this. Okay, here are the facts about these things. That the depth of M is equal to 0 if and only if the maximal ideal is in the associated primes of M. So it's really because if the depth is 0, there are no elements that are non-zero divisors, and that means it's the union of all of them. But whenever you have the union, you can only have a union of a bunch of primes equally the largest one is if one of them is the largest one. So this is using prime avoidance kind of stuff. Okay, but anyway, we have that, and then also the depth of M. Well, each time you mod out by one of those regular elements, it drops the dimension by 1. Okay, so that means that you can keep dropping it down that many of times, and you still get something that's non-zero. So this is less than or equal to the dimension of M. Okay, and the projective dimension over R of M is equal to the length of minimal free resolution. Now you might say, wait a second, why not these are projective dimension? That should be projective modules. Well, for local rings, projective and free are the same thing. Okay, so we have that. So anyway, this depth we haven't talked about over here, but the projective dimension, what's the projective dimension of R mod I? It's 0, 1, 2, 3. Okay, so that's projective dimension 3, but in the localization, it drops to projective dimension 0, 1, 2, or potentially less, but I don't think it could go much lower. Okay. So anyway, so these notions, so this is actually a pretty crucial thing here, and we had talked about this already a bit, that the depth, we did it with slightly different notation, equals, here's the definition, M is called Cohen-Macaulay. Let me do this better. This is M is an R module in this local, in one of these situations here. It's called Cohen-Macaulay if the dimension, the depth of M in M is actually strictly equal to the dimension of M. I mean, not strictly, I mean, is equal to it. And the cool thing here is this depth turns out to be a very homological notion, and this dimension turns out to be a very geometric notion, and these match. And that's the real value of Cohen-Macaulay things, is that geometric and homological notions actually often match. They don't have to, but they do, and that's what's going on here. Now we're coming to the key theorem that has been known for a long time, and when you first learn it, it seemed like, oh yeah, that's like pretty trivial, but after a while you start to appreciate how good this result is. Oh yeah, I did want to do one example just to make sure that we're on the same page with this. This is an example. What's the depth of in the variables x1 to xn of k of x1 to xn. So this is the R, depth of R with respect to that. What's that equal to? Exactly. The variables x1 to xn is a regular sequence. It's not completely trivial that it couldn't be larger. Okay, you need to do some work to do that. If you tried to do it just from straight away basics, you need to use some features of prime ideals, like going up and going down is one way to get at it and things like that. But you have to do something in order to make sure that there's not some. Why couldn't you make a sort of larger sort of set of elements that would give you even more? At any rate, it's you have to think about that. So next thing, that was C, was depth basically. D is the Auslander-Buchsbaum formula. Okay, here is, let's state this as a, here it is, let R comma M be a local ring. You could, or a graded one like that, that will work as well. If M is finitely generated, is a finitely generated R module, and the projective dimension over R of M is finite. These cases it's all finite, but we've also seen ones where it could be infinite. Like if I take k of x mod x squared, then I can get infinite free resolution. So that would not count. But if it's finite, then we have the following very cool formula: the projective dimension of M over this ring R. So you could think of this as a localization, for instance, but it holds very generally. Depth of M into M. Okay. This is actually equal to the depth of the maximal ideal of R itself. Which, by the way, so in our case, what is this telling us? This is so in the case when R is equal to a polynomial ring itself, and let's say M is equal to the maximal ideal. I guess I didn't state it in this case, but it's the same statement that says that the projective dimension over R of M, and in this case everything has finite projective dimension, plus the depth of M and M as defined, that's equal to N. So once you know the projective dimension, you know this, and vice versa, and that's actually really good. For instance, I think we used that earlier to talk about Cole-Macaulay. Instead of saying that the depth is equal to the dimension, we can say that this is equal to the codimension. And that's sort of that we can sort of definitely see from free resolutions and nexts and stuff like that. Okay. Now that tells us that brings us to the next thing, E. Where do I want to do this? Sorry, just a second. Okay, good. I just want to say one more thing about this. So we can define the codimension of an ideal M. So let's say here R is equal to a polynomial ring. Okay. It will also be true for localizations of that and so on. But suppose that M is an R module. The codimension of M is equal to the minimum of the i's such that xi over R of M of R mod I. Actually, wait a second. I've defined this as not just R mod I, as M. M comma R is not equal to 0. So we had seen that before. If m was r mod I, then the smallest one of these was the codimension of I, and we're just using that here. We're only going to need this a little bit to deal with the fact that we are also interested in m's that are X modules themselves. Okay.
Nice description of what X of X is.
X of X. There is an X to X spectral sequence, but I don't know if that probably doesn't quite answer your. Kind of like a dual, actually. In fact, there are some. Depends on what you mean by that. But if I take X of C of R mod I into R, and I take again X C of R mod I of that into R, then I'm pretty much oftentimes getting the same thing I start with if I was, for instance, a prime ideal of codimension C. Okay. For now, this stuff will work in general, but for the rest, now we're going to go into the Eisenbach and Vasconcelos. These are just our building block things that we have to deal with. We're certainly going to be using the free resolution thing, because we're going to be able to use that, because we're going to essentially, this is going to be the picture in mind. We take this, we could drop this down, we're going to know what the depth is. Well, that'll tell us what the projective dimension is, and we'll be able to figure that out. We just have to be kind of careful about it. So what we're going to do now is we're going to assume that R is equal to K of x1 to xn. And we're in the graded case. Or something R equals a regular local ring. Regular local ring is essentially a nice generalization of this, where you don't have to just restrict to the polynomial ring. But this is the case we're going to be using it here. Okay. Although it works for non-homogeneous stuff too. So here's some cool facts. Okay, actually, here's a definition. This isn't particularly a cool fact. Like, support of M, so M is equal to say a graded R module. We could avoid all this graded stuff, but since we don't have that much time, it's easiest to just do it in this case. So what is the support of M, by the way, of a module? This is the set of all P contained in R of prime ideal. So that's really P in spec of R, if you prefer that. Such that if I take M and I localize at P, I don't get 0. Okay. So for instance, e.g., the support of R mod I is equal to the set of all primes P contained in R, which is prime, such that I is contained in P. This is what is usually called the support, because if I is not contained in it, that means that there's a unit in there, and then this becomes the 0 module. Okay. So two notes, so 2 facts about this. Not so hard to prove. One, the minimal elements of support of M are the minimal primes. Actually, I'm not sure I defined minimal prime. I defined associated primes. The minimal elements are the minimal primes. That's essentially that you can take that to be the definition. Minimal elements of this are the minimal primes of M. Okay, that's why it all works. Okay. The second thing is that the associated primes R of M are all contained in support of M. This is finite. This is usually infinite. So, okay. Now we're almost at the point where we can actually state the facts about the Heisenberg Q Vasconcelos. There's a lot more in that paper, and I'm giving you the main idea of it. But there are some things in there that are a little more subtle. Oops, oh, okay. So again, in this case here, when we're in the here and in this case here, so suppose, okay, this is not good. I'm going to trip over this. So if P is contained in R is a prime ideal of codimension. I don't want to use C because I'm going to leave that as a codimension of R mod I or something like that. But is it a prime of codimension J? Then what do we know? Then trying to figure out. I think I'm going to be proving this. Hope I have this all written here. Okay. So then what I want to show is that P is equal to an associated prime of M if and only if P is in the associated primes of X, this codimension J, Xj of M comma R. And we're only going to really apply this for M is equal to R mod I. Okay. So in other words, if I have an associated prime here, so now here, let me do a lemma. I think this will hopefully improve what's going on. So if we have P is in the associated primes over R of M, and the codimension of J, a codimension of P is equal to J. Okay. So if we have that, we want to show that that's the case. Then in fact, two things hold. Then A, xi of M comma R localized at P is equal to 0 for I greater than J. And B, xj, these are all calculated over the ring R, xj of M comma R is not equal to 0. Okay. So this gets very confusing, but the basic idea is that once we have a prime ideal of codimension J, it's going to be nailed. We're going to see it in xj. Okay. If it's an associated prime, we're going to see it. And notice it can't even be in existence in higher x, I greater than j. So so what we have here, let's do a proof of this. I think I don't know if this is quite enough room, but the idea is we're going to use Auslander-Buchsbaum. What's going to really happen, though, is that if it's an associated prime, this thing here is going to have codimension. Everything in here is going to have higher codimension than, or higher or equal to codimension to that number. That means that associated primes here are going to actually be minimal primes here. And minimal primes we can easily get a hold of, whereas associated primes are somehow deep inside the ideal. So so let's see if we can say this in a reasonable manner. So how does this work? So let's suppose that we have this, suppose as in the statement, that P is in the associated primes of M. And the codimension of P is J. Okay, what I want to do is I want to take, I want to localize now at P. So when I localize, what do I get? I guess I want to make sure that, so what is the depth with P, actually this is PRP of MP. What is this? Okay, so we have to go back to the definitions, puzzle that out a little bit, but not really, because what is the depth is going to be, if we have elements in here, I mean, P is in the associated primes. That means every element in M is annihilated by some element in here. That means that every element in P is a zero divisor. But the depth is equal to 0. This is since every element of P is a zero divisor of MP. So the depth is equal to 0. Do you, is this going way too fast for people? So, but think about it here. Yeah, so the trouble is we have all of these notions, and the point is that I've tried to boil it down so that we have all the notions we need on the board, but it is still very confusing to talk about these localizations. But this depth, let's suppose that means, so the depth being 0 just means that every element in here is a zero divisor, which is what it is. I think we said that somewhere. And that was essentially this, okay? But at any rate, that means you have to be grokking the whole bit as we go. But if not, just buy that for the fact. Now, Auslander Buchsbaum, we walk over here, and where is that? Where is that actually? It's up there. It says that now we're applying this in the local ring case where R is R sub P. And then we have the projective dimension. Let's write it down. I'm going to do it over here. So if you could change the camera. Okay, so use Auslander Buchsbaum. I already said that, but now I'm going to really use it. Buchsbaum. And that says that the projective dimension of MP, so this is applied to RP and MP. The projective dimension of this over the ring RP, which we can compute by doing this kind of thing here, plus the depth of that is 0. That's the depth of PRP of MP is equal to the depth of PRP of RP. Now, if you think about this one, this is equal to the codimension of P. Okay. Now, why is that? So basically, R is just like this polynomial ring. RP is a localization of it. And now each one of these things, we just, if we have the codimension, we just keep taking an element that drops the codimension or something like this. And anyway, that we get something along these lines. That means the projective dimension of MP is equal to the codimension. Okay, what does that tell us? But the xi, this is happening higher than j, but the projective dimension is equal to j. So this thing here is equal to j. And therefore, x I of MP comma RP over RP, which by the way is equal to x I of M comma R over R, and then the whole thing done by P. Why is this, by the way? That's the fact that localization is an exact functor. So when the way I compute this, I take a free resolution of M, say, and then I take Homs and I take cohomology, and every single one of those things commutes with P. So when I localize P, that factors into localizing all of those. Okay, so now what is it? This thing is equal to j. So this for I greater than j, then the projective dimension is too short. These are equal to 0. So that means that this thing is equal to 0 for I greater than j. This is actually true for any prime ideal P of codimension j. That they will never appear in this other thing, in this other bit. But at any rate, so that gives us that these are all 0, because that's exactly what that did. But it also tells us that this one has to be non-zero, because once the projected dimension is actually equal to something, that one will always have a non-zero x floating around. So this gives A and B. And that's the end of that proof of the lemma. Okay. That means we have now shown that if P is an associated prime, then it's an associated prime over here. So what we want to do is the other way. Suppose I have an associated, I have a prime P that is in the support of this even. Remember that it's going to be minimal here because if it were not minimal, there would be something else. Wait, no, that's how are we doing time-wise? Anyway, that gives us the one direction. The other direction is the following. Okay, everyone's really quiet. This is a little too fast, but hopefully you can take a look at this. But the paper itself is actually quite a bit harder to take a look at, I think. But maybe you'll disagree. So the other direction, let's see if I can say something about that here. So if P is an associated prime of xc of M comma R. Okay, then I would like to show, and the codimension, I don't know why I changed it from I to J's and so on. That's a little annoying. The codimension of P is equal to C. Then we would like to show that this is actually actually, I can't quite understand what I wrote here. So let's see. So then P is it contains the annihilator of xc of M comma R. Okay. So if I have an associated prime in here, why is that true? I think the reason it's true is actually my argument is just a little fuzzy here. I didn't write enough information down for myself. What I'm trying to do Okay. So what have we shown about these things so far? Okay, if I take xj of this, what are all the primes here that could possibly be in the support of this? What we showed is that really we didn't use the fact that it's an associated prime. This was actually true for any prime. And I'm just messing up my proof now because, but that this is saying that this sub p is equal to 0 if for anything. I do get this confused. I mean, not confused. I find it confusing myself to get the greater thans and less than. So the idea is that here's what I want to say. Okay, I want to say that if I consider, let's ignore this for the moment. That can be. I can't quite figure out what I was trying to say, but so the point here is that so if if we consider any x whatsoever, j of I'm going to just do r mod I just to keep it fixed, but it's for m. Okay, so if I have this and I do sub p, then this is equal to 0 for all p with codimension of p is greater than j. Okay, or is it less than j? You know what? We need to do an example. Okay, so let's do an example. But the basic idea is that what happens here is that, shoot, I didn't, anyway, I'm going to have, suppose that C is, let's do an example. This is not the example, but this is, we'll do an example based on this, okay? So let's start with an example. And I want to take I contained in the ring R, K of x1 to xn. It'll be graded, everything's homogeneous and stuff like this. And I want the codimension of I to equal C. Okay. What are the non-zero x that we have? We have xc of r mod I into R. We know that that's not equal to 0. Okay. That's the definition of codimension, or at least one of the equivalent definitions of it. These are all over R. Xc plus 1 over R of r mod I into R. We don't know if that's 0 or not. When we go up to x to the projective dimension, I'll just write PD of R. So this is PD of r mod I into R. And this one is not equal to 0. These in here could be 0, could be non-zero. The top, this one is never 0, this one is never 0. If they're both, if this is equal to this, that's the notion of Cohen-Macaulay, and everything's the same. Okay. And what it happens is that every prime ideal of this thing has codimension equal to C. Here, it has codimension, there could be stuff of codimension C plus 1, but I'm getting confused as to whether it should be the lowest codimension stuff is at the top. So this could have higher codimension stuff in it and not that. So what's happening is we have all of these things. If I have a prime that's non-zero here and is of codimension exactly that, that is going to be an associated prime. Okay. So what I'm saying here is that if I have an associated prime of this guy of codimension J, P is of codimension J and it's the same J, then it had to be coming from M. Okay. And now I want to do, let's try doing an example of that, if I can get back on in a short amount of time. So could someone else push the screen down? It'll just take me a little bit to get back on. In fact, I will go back to Arthur's email. I don't see it here. Here it is. Nope, that's not it. Okay, where is it? That was sent probably close to 10. Here it is. Oops. It wants the meeting passcode again. Does anyone happen to remember it? Yeah, it is. I got it.
If you just move that little block, it should be behind it, yeah. Oh,
Okay, let's share. We'll just share the Emacs one this time. Okay. Okay. Now let's do week 11, and we're gonna, whoops, not there though. Come in here, gonna make week 11 EHV. .m2. And we're gonna take an ideal that has two associated primes, I think. So here's one way to do it. So I'm going to do R is equal to ZZ mod 32,003. We can do Q as well. A dot dot D. We'll just take something in four variables, like a curve. And I would, in fact, why don't we let it be monomial curve ideal of R comma 1, 3, 4. Okay, but that's not the ideal we're going to choose. We're going to intersect that with something that sits inside of it. Okay, so I think the ideal ABC sits inside of it. So I'm going to do I comma ideal. If I do ideal of ABC and intersect it with this, I should get I back again because I is actually contained inside of that. But if I instead square this guy, for instance, and I call J is equal to this, I get some ideal now in here. And now if I do primary decomposition of J, I get two things. I get 1, 2, 3, 4. This is the this thing here is the rational quartic curve. There's 4 generators, so 1 quadric and 3 cubics. And then we have here, you want that to be larger, right? Is that okay? That's good. And then here we have, I had said that the ideal was this ABC squared, but it found a different one, A comma B squared. I mean, the trouble is it's not unique. It's an embedded thing. But nonetheless, it if I do, let's see, if I do, this is comps of J, and if I do comps of J / radical, those are my associated primes. So now we're going to calculate the free resolution of J and just look and see what we have here. So if I do J, so if I do F is equal to resolution of J, okay, it's 6, 7, 2. Okay, 6 generators, and then it goes up back to this point here. Okay. By the way, let's take a look at it. F dot DD. Notice that ideal was ABC, by the way. Actually, that's interesting. There are no ABC. You can't just get rid of this. If your prime that we wanted to localize by was ABC, there is no element in here that's a unit. So we're probably not going to get rid of those. How about here? Are there any elements here that it's a unit? Actually, there is. This one is a unit with respect to ABC. So that's the 4th one. So it's a little bit peculiar what happens, but nothing else is a unit in here except for that one. What that tells us is that we could get rid of one of the generators of these 6 locally. But we're not going to do that right now. Instead, we're going to calculate X. What's the codimension of J, by the way? It's 2. Okay, it's codimension 2 in 3-dimensional space, projective space, which is a curve. And so if I do, if I take X2 of R to the 1 mod J comma R, okay, I get this module here. Now, if I take its annihilator, what do I get? I get exactly the curve I wanted. This is another result of the Eisenberg-Hunicke-Vasconcelos. If I want the top dimensional parts of I, that means the intersection of all the components of top dimension, that is the same as the annihilator of xc of this thing. Okay. So this is equal to j is false.
Yeah.
Oh, I. That's true. Okay, good. Okay. Now that, okay, but that was the easy one, right? That's the minimal prime of I that we can get by taking radicals and seeing what's going on. And the other stuff will probably go away at that point. We'd have to check on that. But we have all these techniques for doing that. But what about x3 of r to the 1 mod j? Oh, maybe we better put two things in it. And we get this. Okay. This is actually kind of interesting. So, so what are, if I take the annihilator of this, what do I get? Let's call this E3 for the annihilator of x3. I get A, B, C squared, and C times D. So there is one minimal prime here. This is actually a good example because the things that I was getting confused about there is actually showing up here. This is showing that I have two that I'll have two minimal primes of this thing. At least, I mean, actually, let's do primary decomposition of that. Primary decomposition of E3 gives me two things: A, B, C, and then another one, A, B, D, C squared. This thing ABC has the same size as 3. That is telling me right off that this is an associated prime. This one has dimension greater than that, but it's not an associated prime. Or it might be, but we don't know that. It's just there. So really what we're doing is we want the top dimensional part of each one of these x's. And every single one of the primes of that, the minimal primes of that, will be the associated primes. Minimal primes, we already have all these great ways of doing it. So that's the way that the Eisenberg-Hunicke-Vasconcelos thing works. What about x4, by the way? Or maybe that had resolution 3. If I come back to look at the resolution, yeah, it was length 3. So there is nothing higher. So that actually tells us right off the bat that there are no associated primes of length 4. There's only one homogeneous length 4 associated prime, which is all the variables. And that one is going to be an associated prime exactly when the depth is 0. I mean, when the thing is not saturated. There's lots of, we can sort of see that that can't be the case. So anyway, so what I could do is I can take, here's how I can get the top dimensional part of something. I can take, here I have x3 is just a module, right? How do I get the top dimensional part? I want the ABC. I mean, I can see it right here. ABC, this generator is just that mod ABC. This generator is that mod A, B, C, D, and C squared. Okay, so this X is really a direct sum of two things. And so, but what I can do is I can take X3 of that module, okay, comma R. And look at that, it gave me now, it stripped out the lower dimensional stuff, and it gave me two copies of this ABC. Well, I mean, so that, you know, we saw it anyway before. Now we can do annihilator of this, and we get ABC. So, so really, this is the way. This thing here doesn't give you all of the minimal, all the primes. It gives you an ideal that has no embedded primes, and that basically, it just has whatever primes are in it are exactly the primes of codimension 3, the minimal, the associated primes. I think I'm going to kind of leave it like that. This thing here is actually not bad. It's just a matter of when you localize by something, then you have to say, okay, wait, what primes actually could it be non-zero at and 0 at? And I mean, I was getting confused, and if I'm getting confused, it's not, you know, yeah, I think that it's almost better, the example I think is hopefully better than that. But it's just kind of cool that all of that, I really like to think of it as bubbling up. You have all these associative primes that are deep down under the ground that you can't see. You can see the minimal prime oftentimes, but the other ones are underground. Then when you take the X, the second, the XC is the one that is already there. XC plus 1, then any associated primes of that bubble up to the very top dimensional part of that. So you can compute it using this annihilator of that X. And then each time you have them bubbling up, and you can get them all. And oftentimes you can use theory with the X to rule out lots of things. So computationally, it's not so bad. Okay, anyway, that's that. So I think that for the next, okay, it's 12:30 now. So I suggest now we do project time. I suggest 2 things for the projects. One of them would be to create a package and things like that and get that going. The other one would be to do the free resolution over localizations, problem 4 on this list. Just to sort of go through, and it's essentially taking the one example I sort of did a little bit and actually really taking a look and seeing if you can write down the free resolution over each of those 3 primes of that. And then you see the dimension drop and things like that. And I would sort of do it in Macaulay 2 to get the resolution of it, and then by hand to sort of try to do row and column operations on that. Does this sound like a reasonable plan? As far as problems 2 and 3 goes, actually problem 3 is a good one too. That one doesn't need anything that we haven't done yet. So if you want to do a slightly more theoretical thing, here are a bunch of potential splitting principles that one has. The first 2 we actually proved already in class at various times. Then C, D, E, F, G, H, some of them are true, some of them aren't true. So which ones might that be? And if you can prove the ones that are, and if not, if they're not true, then find a counterexample. So that's a nice sort of theoretical one if you need to change of pace for it. Okay. And then let's get back together at a quarter, no, at 10 of. So give you, that's not so much time. Let's just get back together and talk at 5 of. And we'll just sort of, say things. And then you can say if there were any difficulties with it, and we can either talk about it or say what to do next time.